Log on, tune in, find out. Another good idea from Cambridge.
Donaldson compactification for frame sheaves.
Thank you. Can you hear me by the microphone?
It's both of the recording line and the
Yeah, sure. Okay. So actually, I gave the same talk at Teklov Institute in Moscow last month, and it was recorded. It's available on the internet. So this is becoming a bestseller of the internet. So thanks a lot to the organizers of this meeting period for inviting me here. It's really very nice. And I should mention, before I forget, that this is joint work. It's partly together with Dmitry Markushevich. And this part can be read in this archive preprint. And part with Dmitry and Alexander Tikhomirov. And this part can be read in this paper. I should also say before starting that the title refers to a compactification, Uhlenbeck-Donaldson compactification, but as we shall see, this is not a compactification. It's a misnomer. It relates more to what, from the differential geometric viewpoint, is a metric completion of a modular space. Anyway, this will be clear, I hope, during my talk. I'd like to start with, as a motivation, I would like to start with the simplest case, which is very classical, perhaps maybe a little bit boring and elementary, but I mean, then one can understand what I'm trying to do in the general setting. And the classical case is the correspondence, is the modular space of ideal framed instantons on the fourth sphere. So, so we start from the fourth sphere, say with the usual round metric, and we consider on it a principal bundle, P with some structural group G, and we assume that G is the group SUR. We fix a point in the fourth sphere, and in the fiber over it, we fix a point. So the point and the fiber of some preferred point on the fourth sphere, it's called the framing. And we want to parameterize pairs. Sorry, I should first say that, of course, topologically, the bundle P is classified by the integer R, and its second Chern class in some sense. For instance, we may introduce a rank R vector bundle, which is just obtained by the standard representation of SUR over CR, and we fix the second Chern class of this bundle. We call it N, and this is called the instanton number of this bundle. And then we want to classify pairs, nabla phi, where phi is a framing in this sense, and nabla is a connection on this principal bundle, which is anti-self-dual, in the sense that you take its curvature, you can apply the Hodge dual operator to it, and we want this to be minus the curvature itself. So this is an anti-self-duality condition. So we want to parameterize such pairs. And of course, modulo gauge equivalence, namely vertical automorphisms of the bundle P which fix the framing. And then it is a classical result that the modular space that you get from the set theoretic point of view may be interpreted as a space parameterizing some spatial bundles on P2. This is due to Donaldson. So if we consider the framed SUR instantons, as such pairs are called, on S4 with the second Chern class, fixed second Chern class, modulo, say, framed gauge transformation. This is one-to-one with a set which parameterizes rank R, holomorphic, vector bundles, framed vector, vector bundles on P2 that are framed with second Chern class N, that are framed on a fixed line in this P2. Modulo isomorphisms that are compatible with the framing, with the isomorphisms. Well, I will write an equation about that. So we have framed isomorphisms. And by framing, I mean that if we take such an object and we restrict it to the line at infinity, there's an isomorphism with a trivial bundle on it. Okay, so this is the framing in this context. And then it's a result due, an 84 result, if I remember well, due to Donaldson, the fact that there is a bijection between these two sets. So just to introduce some notation that I will need in a moment, and I will basically...
Stability condition?
Sorry?
Some stability condition is not needed?
No stability condition. Actually, part of my talk is to show that this includes some stability condition automatically.
Oh, just you take only framed one.
Framed, yeah, framing. Yeah. The framing is a stability condition in a sense.
So you have not put the other connection.
Anyway, the theorem is correct like this. There is no need of any additional stability condition. So this is the first personification of this modular space. I will say I'm going to use Nakajima's notation, if anybody is familiar with them. And this other set I will call MLF, of course, for locally free. Now this space of frame instantons is a natural pseudo-compactification, which is indeed the Uhlenbeck-Donaldson compactification. The misnomer comes from the fact that if you do this in the non-framed setting, then you get a true compactification. This is the standard compactification of the modular space of usual non-framed instantons in that case. In this case, what you do is the following, very trivial, very elementary, in a very elementary way, I mean. Suppose that for such an object, you consider, say, the norm square of the curvature as a function of S4 or R4 if you remove the point where you make the framing. So this is R4. You get something like this. And at least for some configurations, in the sense that you have an n peaks like this, which are, I mean, if they are far enough that we may consider that the, so to say, elementary instantons are weakly interacting, you see this structure with n peaks. And the idea is that you can allow one or more of them to degenerate, to shrink to zero size, and due to the normalization, when such a peak shrinks to zero size, it goes to infinity. I mean, the height goes to infinity, which means basically that around this point, this, regarded as a measure, approaches the Dirac delta. Okay, you do that. So you consider all situations where one or more peaks have shrunk to zero size. One can show that this is equivalent to, I mean, this, you can give some structure to this modular space, for instance, by using ADHM data, and this comes with a natural metric, and you are completing the space with respect to that metric. And this, using ADHM data, you can also see that this is a variety smooth variety. But when you do that, you perform this operation, what you get is a singular variety. So what happens is that this space sits inside as the smooth locus, and n0. What happens is that you can shrink one or more of these peaks, and correspondingly, I mean, this corresponds to a stratification of this space, a set theoretic stratification, at least to start with, of this space, which can be written like this. When you shrink one peak, you decrease the second Chorin class by 1. So here you have something like this. And once an instanton, I mean, a peak has been shrunk, only the position matters. There is no other parameter, and therefore you get, identifying R4 with C2, you get this. Okay, so we have this stratification, and this is, in our case, the Uhlenbeck-Donaldson compactification. As I was saying, this is singular. You can blow it up. You do the blow up. You get some object that one calls Rn. And what's interesting here is that this space is itself a modular space. And indeed, it parameterizes torsion-free rank R framed sheaves OP2. Exactly, I mean, according to this situation, but allowing the the sheaf to be torsion-free, not only locally free. And indeed, what happens is that here, that the modular space, Donaldson modular space, will sit inside as a complement of the exceptional, in the inverse image of the exceptional locus, and these are identified. Okay, so this is the situation for S4 versus P2. And
would it be fair to say at this moment that M0 is not a modular space?
What do you mean?
It's the course one.
Well, actually, what I'm going to do will completely describe what this space is.
It doesn't make it a modular space.
It doesn't make a modular space in a strict sense, yeah, indeed. Particularly, we show that in general, the Uhlenbeck-Donaldson compactification that you get is a quotation mark modular space of mu semi-stable frame sheaves, which is not a modular space in a full sense. It doesn't represent a functor.
No represents.
Sorry, no,
Coarsely, yeah. Not even coarsely.
not even coarsely. No, as a mu semi-stable, it doesn't. Of course, okay, I will go to that actually. That's what I want to say. The point is that what you define in that way cannot be constructed as a GIT, as a categorical quotient. It's a, well, do you know Jun-Lee construction of the same object? This is very much along that line.
I mean, it is a categorical quotient of ADHM data.
Sorry?
It is an ordinary GRT quotient of ADHM data.
I don't understand really from an acoustic viewpoint. I'm sorry.
Then we could talk
Okay.
later.
Okay. So actually, the idea is to define the. I mean, I want to have what I will do will work on surfaces. To start with, I can just for the first definition and to give some general. To make some general construction, I can assume that X is a smooth projective variety of any dimension over C. I assume I have a polarization. And I fix, once for all, a coherent O module. And I want to study pairs if E, where E is a coherent OX module, and phi is a morphism from E to F. So F is fixed, and I study such pairs. And the idea is that to start with, I allow F to be any coherent sheaf. I don't make any assumption about whether it is concentrated on some subvariety or whatever. And then there is a notion of stability or semi-stability for such pairs, which is due to Albrecht-Einstein. And as we know, every time we parameterize semi-stable decorated objects, pairs, triples, whatever, some parameters come into play. And in particular here, we fix a polynomial with rational coefficients, and I assume, to make the theory nice, that its degree is the dimension of x minus 1, and that it has a positive leading coefficient. And basically, the idea is that when you give, as usual, we want to give a notion of semi-stability by testing what happens when you consider a sub-object. And here, it's natural thing to do is to give a different prescription according to whether the sub-object is in the kernel of phi or not. In order to do that, we simply introduce an object epsilon of phi, which is 0 if the framing is 0, and is 1 if the framing is not 0. And introduce a Hilbert polynomial which takes the framing into account by considering the usual Hilbert polynomial and subtracting or not according to the value of epsilon the polynomial delta. And then the idea is that a pair is semi-stable if for all proper subsheaves any subsheaf will inherit framing from E, and then you require this to be true. Okay, I'm a little sloppy here. Okay, and if you spell out this according to whether E prime is in the kernel of phi or not, you get two different explicit writing of the stability condition. In the same way, you can introduce mu semi-stability by introducing a frame version of the slope. In that case, what you need is just a parameter that I will call delta 1 to avoid the confusion. You consider a positive parameter, delta 1, and you have a notion of mu stability, semi-stability, and there is the usual chain of implications between mu stability, Giesecke stability, Giesecke semi-stability, and mu semi-stability by identifying delta 1 with the leading coefficient, the leading coefficient of the polynomial delta that you use.
Well, the formula doesn't have the right, not grammatical. You mean equals something minus?
Oh, this is complete nonsense, sorry. Thank you. Okay. Now, of course, you can define you can define consider the obvious moduli functor for either semi-stable or stable frame sheaves in the Gieseker sense. And what Uhlenbeck and did was to prove that there exists a projective scheme which I denote. Well, if you really want to keep track of everything, you should write something like this, okay? Where f is the framing sheaf I fixed from the beginning, p is some polynomial I fix, and also I fix the polynomial delta, and then this scheme will parameterize the moduli functor of the semi-stable pairs of semi-stable sheaves with Hilbert polynomial p framed by f and semi-stable with respect to the polynomial delta. So this co-represents the functor of semi-stable frame sheaves in the usual sense. And what happens is that inside there's an open subscheme which parameterizes. Well, in a moment I will stop writing all this stuff. Parameterizes the stable objects, the stable pairs, and this is a fine modular space for such objects. Okay, this is the result by Uhlenbeck and Len. Now, this will be an answer to the question about stability, whether you need any stability condition for framed bundle. And the idea is the following, that you see that what we did.
This is irreducible?
In general, I don't think so. No. It must be studied by cases, I guess. No. Not that I know. So the stability depends on the choice of polarization, of course, and the polynomial delta. In particular, we study a situation where X is a surface, and we consider some special kinds of framings, which, on the other hand, are, the framings that one encounters in practical situations, so to say. So now X is a smooth projected surface. I choose a big NF divisor in it. And I take a semi-stable bundle on it. Actually, the theory works under a numerical condition which is somehow weaker than semi-stability, but really it's a very small generalization, so we don't bother about it. And
Semi-stable in some sense on beginnings.
well, let me assume that this is irreducible. Then this is a irreducible curve, and okay, it can be done more generally, but let me do it in a simple case. And we assume that the framing that we are considering, if we restrict it to D, is an isomorphism. Okay, so we restrict to such a situation, and then one can prove the following. And this is indeed what was done in the first paper I cited. That for all choice of topological invariants, so for every choice of an element in the Chow ring of X, there is an ample divisor in the rational number delta 1 such that all frame sheaves that satisfy these conditions, I mean the frame sheaves I'm considering under these assumptions, are mu stable. Okay, so I mean, when we consider the beginning the space of all framed bundles or framed sheaves on P2, there was no stability, there was no polarization, there was no delta. Okay, so the idea is that when you have such a space under these conditions, you may choose a polarization and a parameter in such a way that the objects we are considering are automatically mu stable. As a consequence, we can obtain a modular space for such objects just by inheriting the structure from the Uhlenbeck-Donaldson modular space. This is a subset according to this result of the modular space for this choice of H and delta 1. And in this way we get actually that this space is a quasi-projective moduli scheme for these frame shapes. So in this sense, I don't write the whole story again for these frame sheaves I'm considering.
You really mean stable?
Sorry?
You really mean mu stable?
Yes, I do.
So what are the mu semi-stable ones?
Mu stable one, I'm going to construct
Semi-stable ones you're going to
to construct a space which parameterizes them in some sense. That will be the Uhlenbeck-Donaldson compactification. Of course, in principle, they are not inside the modular space, Uhlenbeck-Donaldson modular space, which is just Gieseker semi-stable objects. Very quickly, let me just mention that you can develop some deformation infinitesimal theory, and it's very easy to show that the tangent, let me just call MC this modular space without writing all parameters. It's just the first hyper-X between E and the complex given by the framing, and this of course is just x1 E minus D. Okay, and you can show that the abstraction to the smoothness lies in the kernel of the trace map from the corresponding second X group to the second cohomology of minus D.
Up there, when you say this is isomorphic to x1 of E minus D, do you assume that F is the structure sheaf of D or something? Otherwise, it seems to be independent of F.
Yeah. Oh yeah, sure.
No, but F is
Yeah.
E restricted to D.
Oh, I see.
Yeah.
I missed that. I'm sorry.
Yeah.
I see.
Could I ask a question about your theory? So this is Gieseker stable framed guys, is that right? And they're slope stable sheaves.
What do you mean? I start from something which is just frame sheaves with no stability condition.
No stability.
So no H, no delta. And I say that I can choose H and delta in such a way that all of them are mu stable.
implicit stability condition is the fact that this map is an isomorphism.
Yeah.
I see.
Otherwise, this doesn't work.
Yeah, restriction.
Yeah, yeah, absolutely.
That's the open condition.
But F is only semi-stable. Yeah. Okay. Great.
Then you take F to be the trivial bundle, for example, in this.
Yeah.
And this is on a surface or in arbitrary dimensions?
Surface.
Surface. I see. So it's a bit like so Donaldson parameterized mu stable bundles by saying whether or not they restrict to a very ample curve. He mapped to the moduli bundles on the curve.
Mm-hmm.
I see. It's kind of like
Yeah, it relates to that, yeah. Mm-hmm.
In Donaldson's, the paper doesn't fix any stability condition, just the framing is enough, that's what he said.
Yeah.
On P2.
Yeah, yeah. You know, now I'm citing some examples, but there is, what Alastair did in his thesis is related to this, right? You studied framed bundles over P2 blown up at one point, no stability condition.
It's the isomorphism of E restricted to D with F.
Yeah,
It is.
yeah, of course, yeah. And this may be generalized to P2 blown up in several points to Hilbert surfaces. And you can what I mean is that you may construct such modular spaces in a rather explicit way. These examples I mentioned are all covered, including the case where you allow for degenerations to torsion-free sheaves by ADHM constructions, which this is done for P2 blown up at many points and Hilbert surfaces. Has been done by two different students of mine, and the papers are appearing. One is already on the archive. And the other is going to appear.
But then you want to get a moduli space of mu stable guys by taking the moduli space of framed sheet.
No, this is inside. What I want to do is to give a scheme structure to the modular space of framed sheaves by resorting to the fact that a modular space for mu stable pairs with respect to fixed H and delta exists by Uhlenbeck's length theory. Then I say that I start from some framing with no H and delta. I can choose H and delta in such a way that all these framed sheaves are mu stable in the sense of Uhlenbeck's length.
And then are they semi-stable framed sheaves?
There will be the points of the compactification.
They're automatically stable framed
No.
sheaves.
There will be semi-stable points that you will be now adding
I mean,
to compactify this object.
so they, they are mu stable, so they are also Gieseker stable. They are in general not necessarily. They are mu semi-stable, but of course there are mu semi-stable sheaves which are not here.
No, I'm just wondering if they appear in Huybrechts and Lane's moduli space. These guys.
Yeah.
These ones.
This is the point. This is a subset. As such, they get this modular space.
The polarization is able to give an embedding of that inside the Huybrechts lens space.
Because Huybrechts and Lane also have, but they have a stability condition.
That's
Indeed. Indeed. What I'm saying is that you can choose H and delta in such a way that our frame sheaves are stable with respect to Huybrechts and Lane. For that choice of polarization and delta. Delta can be moved in some, there are chambers, whatever, but the idea is that you can find such on H and delta.
All this is being done only to give this a scheme structure.
Yeah. Correct. And by the way, in the examples I mentioned, P2 blown up at several points, Hilbert surfaces, you can give scheme structures also using ADHM conditions, but then, description, but then you can prove that the two scheme structures are the same. Basically because in both cases, this, I didn't say that, but it's a automatic corollary of this construction that this modular space is fine. And what you build with the ADHM constructions are fine modular spaces as well, and therefore for universality the two scheme structures coincide. So indeed, examples. The simplest example is when R is equal to 1 and F is just the structural sheaf. In that case, this trace morphism is an isomorphism, so there is no obstruction. But actually, in this way, we are rediscovering the fact that if we subtract the framing divisor from X and take the Hilbert scheme of 0 cycles here, this is moot, because in this case, the modular space is exactly this. Okay, so this is the first example. And the second example, it's the situation to which all those cases I mentioned belong to, in the sense that you may prove that if this is true, and f is trivial, then that condition is satisfied. And therefore you get smooth modular spaces, and these are exactly the case of P2, Donaldson case, including also the generations. So the modular space of torsion-free frame sheaves constructed by Nakajima. P2 blown up at distinct points. And Hilbert surfaces. For Hilbert surfaces, let me cite something which is not, it's something which is not proved using these techniques, but let me just show you that one can give at least in some cases, a very explicit construction of these modular spaces, and I will need this as an example of my final statement, provided I will ever get to it, of course.
Why are the two dot sheaves in that?
Say, sorry?
Plus,
Why
I
are the two
think.
dot Ds?
The first is a plus.
Plus.
Kx plus.
Oh, plus.
I'm sorry. Of course, it's a plus. Yeah, sorry. So let's consider the pth Hilbert surface, and in that case, what you construct is something that we may write in this way. So I'm assuming this is correct. Sorry, is a line. It's a rational curve square into 1 in the Hilbert surface, and then you can parameterize these modular spaces using these integers. In particular, k is, let's say, the value of the kth first Chern class. Sorry, it's the value of the first Chern class in the sense that the framing forces it to be the first Chern class to be a multiple of C, where C is the curve which is rational curve which squares to minus p in the Hilbert surface. And n is the discriminant. And this, this may be described in full detail using ADHM data. This was done by my student Claudio Rava. And in particular, you can show the following. There's a special value, a special combination of these invariants, in particular the number pk over 2r times r minus k. And you can prove that the modular space is non-empty if and only if this inequality holds true. And in the case where n is equal to n, capital, so the lower bound, the modular space is very nice. It's a vector bundle over a Grassmannian. And in general, for this modular space, you can do instanton counting. This is another paper in some other work with other people. And in particular, it shows that, well, this is smooth by our criterion, and you may show that this is irreducible. It's connected and it's irreducible for all values of the discriminant. Using instanton counting, you can compute the Betti numbers of this modular space, and then you get this. Okay. Now let's go to the Uhlenbeck-Donaldson compactification or pseudo compactification. So the idea is the following. We extend a little bit the code scheme that one uses to build modular spaces using GIT theory by adding something which parameterizes the framings. So the idea is the following. We consider, these are the usual implements of GIT construction of modular spaces. We consider this space for m big enough. We call it V, and then we consider the possible homomorphisms from V to the space. Take dual and projectivize, and we call this P. And this is basically, this describes the framings. So of the trivial sheaf V times the structural sheaf. So in particular, an element here induces a framing for H, which is V times OX minus M to F. And then, no, this is fixed, sorry. It was a little hard in it. But I need more space. Here I must be very sketchy if I want to get to the end of it. And the construction is not particularly new. So the idea is that inside the code scheme, parameterizing quotients of H with Hilbert polynomial P times P, I consider a kind of incidence variety that I call fat quot. In principle, this depends from, this depends from F as well. And the idea is that these are pairs. Well, actually are triples, because of course an element in the code scheme is a pair itself, so they are triples such that phi phi from G to F exists, such that for which we have this situation. And then Uhlenbeck-Donaldson construct their modular spaces using this kind of quad scheme. In particular, what happens is that there is a boundedness result due to len, which says the following. Well, okay, which says that if you consider the family of Gieseker semi-stable frame sheaves, these are bounded, and we may construct the modular space by GIT theory. But what happens is that also if you consider the mu semi-stable, so this is the family of mu semi-stable frame sheaves, this is bounded as well, and you may associate with it as a subscheme of the fat quad scheme, and this turns out to be locally closed. And then the idea is that using is usual the determinant line bundle on the quad scheme and the suitable multiple of the hyperplane bundle in P, you define on this a bundle which linearizes the action of the special linear group of rank of order Pm. The problem is that this is not a good GIT construction. This line bundle is not ample, you can prove it is bigger than f. And here there are points which are not GIT stable. So in principle it seems we are stuck, but what you can do is that you define a modular space by hand, so to say. And what you can do is the following. You take the projected spectrum of this object. This is the line bundle I was alluding to. And then you take a cell invariant sections. And the idea, this is the replacement for the non-existing, in proper sense, modular space of view semi-stable object, or sheaves. Now, this doesn't satisfy universality property in a proper sense. It satisfies a weaker universality property.
It's also not projective, right? It's not proper.
Sorry, yeah.
Still prove it's proper or something. It's projective. There's nothing like that. Isn't it projective right?
No. No, very clear. It will be very clear by the examples.
Generally it won't be.
Let me skip this weak universality property, which has really no particular importance. So let me go to this point. I mean, this space is, in the sense that I will show now, is a kind of stratification, which shows, its structure to some extent. The point is that all Giesecke semi-stable sheaves are mu semi-stable. So this means there is a map from the modular space of mu of Giesecke semi-stable. The Albrecht-Len modular space to this. I will drop or C's and delta. You have a map like this. And you can study the fibers of this map. This is what I will do in a moment, and this will give rise to a stratification. You can prove the following, by the way. Inside MSS, you have the subscheme of the mu stable. And gamma restricted to this open subscheme is an embedding. So gamma is an embedding if restricted to this. Then what you can do is to take the image and close it inside mu MSS, and this is the Uhlenbeck-Donaldson compactification of the modular space of mu stable. So this mimics what one does. This is the algebraic rendering of how to construct the modular space. The Uhlenbeck-Donaldson compactification just for sheaves. Okay, so you give such a partial compactification of the modular space of mu semi-stable sheaves. And of course, our modular space is inside, so you can do the same with it. You can close it. Instead of the full modular space of mu stable, you can just close our modular space, so to say. In that way, we get a Uhlenbeck-Donaldson compactification. What happens is that one can describe the fibers of this morphism in the following way. One needs the following fact, that for these sheaves, there are Jordan-Hölder filtrations as framed sheaves, satisfying the usual properties. For mu semi-stable in particular, for mu semi-stable frame sheaves, one has Jordan-Hölder filtrations. And then you can prove the following. I will use this notation. Script E is a pair, frame sheaf. with a fixed invariant that we fixed from the outset. And then you can prove that E1 and E2 are in the same fiber if two things happen. The first thing is the following. You take, say, E1, you compute its Jordan-Elder filtration. You take the graded object in this sense, and you take double dual. Now this is locally free, since we are on the surface, and then this should be isomorphic to the same object obtained with E2. And then with this technique, you also single out some bunches of points. I don't want to write too much, so let me simply write SP, and then I will say what it is. It's the obvious thing, but anyway. These are subsets of a symmetric product of the variety. Actually, the variety minus the framing divisor D. So due to the framing, E is locally free on the points of D. And this is, so SP of E is just, I mean, the points where the graded is not locally free. Sorry. The support of this. Okay, so 2 points belong to the same fiber if and only if they satisfy this condition. And actually what happens is that these double duals are mu polystable, and then this gives rise to a stratification of this, a set theoretic stratification of this modular space in this way. So here I specify that I fix topological invariance C, and here what we get is sum over the possible values of K. I write C minus K, I mean that I subtract K from the second Chern class, times the symmetric product of K copies of X minus D. And the same is true for, for this you can also imagine the Uhlenbeck-Donaldson compactification of our modular space. So you see that this is not projective because we have a clear idea of the structure of these pieces here. Let me just mention that there is a slightly different behavior which makes this modular. Of course, in general, these modular spaces are quite complicated. Let me just compare the situation that you have with P2 and what you have for Hilbert surfaces. So for P2, the Uhlenbeck-Donaldson compactification is what I write at the beginning. I wrote in the beginning. In particular, it has the structure. And here K goes from K to N. So the deepest stratum you get when N is equal to K, K is equal to N, and then this is a point, just given by the trivial bundle. So this means that the origin of C2 counted n times is a point. On the other hand, we have the modular space of all torsion-free frame sheaves on P2, which is a resolution of the singularities of M0. So here you have a kind of Chow-Hilbert morphism, and you can take the inverse image of this, and for instance, you can prove that this is homotopy equivalent to the full modular space. There is a retraction from the full modular space to this. This is a quad scheme, by the way. It's just a quad scheme of I mean, quotients rank 0 and the length n of the structural sheaf, of the trivial bundle, sorry. Suppose we consider now this is a vector surface, and we have in that case we have a stratification like this, but in this case the smallest stratum is not a point, is the minimum value is given by the minimum value of the discriminant for which you have a non-empty modular space. So here we shall have something like this. Fp minus the framing divisor. This is the total space of O minus P over P1. Correct. If you remove a rational line, as I chose at the beginning, you get the total space of minus P over P1. And therefore, a result like this is definitely false. And one could study how the topology of the full modular space and the topology of the deepest stratum here are related. And I think I will stop here. Thank you very much.
Any questions? If there are no questions, then can we
Thank you.